Good morning, everybody. My name's Ken Grob. I'm with Elma Electronic Inc., and pleased to be here. It's nice to be able to actually put on a full outfit and wear a suit and not sweatpants. So today, I'm taking a little bit of a different tack. Usually we get up here and talk about bits, bytes, and all sorts of neat stuff like new protocols and all that. Had some really great introductory presentations just preceding me with some really interesting information about 100 gig and how we might get to fiber. Today, what I wanted to do is sort of keep it light, but look a little bit from the top down and see who's driving us to invent all this great technology and look a little bit more at it from the application focus, and also, in another sense, to look at what we got done in the last 2.5 years where we're all working through an interesting pandemic world, and were we able to really get anything done? So let's dive in and see how that goes. Live in La Vida MOSA, ETT23. This is really like a chronicle of the MOSA journey. A little bit of background, some initiatives that the services are conducting, the tri-services, and then looking at the efforts of the SOSA Consortium and industry to support those initiatives. A few things about trends, and then a look at what's next. So, have a couple slides about Elma. It's been 2.5 years. I start to forget faces and names, and then who's doing what, so I just wanted to remind everybody what we do and who we are. We got about 800 people worldwide, annual revenue about 150 million. This year has been difficult with supply chain issues and all that, but overall, given all the challenges, we did do fairly well in bringing in a few orders and developing a backlog, so I think we'll have a reasonable shot at the year. What do we do? Just to remind folks who may not be aware of Elma Electronic Inc., we're in the rugged computing business. We build packaging and backplanes, chassis managers, and we also get involved in integration that's focused to the aero industry. So I wanted to start sort of from the top and remind us what MOSA is all about, since we're talking about the Chronicles of the book of MOSA. And I heard the idea came for this talk from a guy who found an envelope in Dayton, Ohio by a tree, and wanted to see if this format would work in trying to get the message out, because we're starting to run into things like SOSA fatigue and MOSA fatigue, because we hear a lot about it. So we want to look at it, see what those guiding principles are from MOSA. This comes from an old slide from the Open Systems Joint Task Force, where they're talking about 5 principles of MOSA for the acquisition community and the benefits of those principles. And this really becomes the informing directive for what's been done in SOSA over the last 5 years. So if we look at SOSA by the numbers, this is pretty interesting, and it's kind of refreshing, because if we look at, were we going to be able to continue to make SOSA work during the pandemic and how we're going to make that happen, it was amazing what took place relative to how quickly SOSA and the open group and all of the members who participated were able to adapt to continue to keep things moving. If you look at that top line, SOSA has now increased to 144 members, and back in 2019 we were 74. So if there was any questions about whether the coleslaw was still being made, it looks like it has been, because SOSA has practically doubled in the last 2.5 years. So if you go down here, we have a new sort of infographic coming out of a business working group within SOSA that's highlighting the process, and then we can see the tri-services are represented down here by these logos, CMOS, Host, and OMS for the Air Force, and then the cooperation with VITA. And then to highlight sort of 4 of the important guiding principles that SOSA is about, is building better platforms, collaborative environment between government and industry, and this one, last 2, I heard in the last 2 topics, this is really important, ensure interoperability and mix and match vendors, which is no small challenge. So, given a little bit of a sort of a scorecard, or looking at where SOSA is, today we got edition 1.0 released in of the technical standard released in September 2021. And what's in process is Snapshot 2, version 2. And this is sometimes, even for the people that are participating, hard to remember because you get buried in what you're doing in your working group and you forget where you're at. So it's so good to kind of go back and look at where we're going. At the same time, what's been done? We've got done, or SOSA's got done, the business guide, and some of this is coming out of the BWG, the business guide, the supplier guide, and the marketing guide. And what's in process right now is something called the RIG, Reference Implementation Guide, and understand this is right around the corner, which is an interesting document that gives reference information for system integrators and sort of how-to and guidance. And this has been worked on for quite a few years now, and I think it'll be a great tool for industry to use. And then also an acquisition and contract guide. So partners in crime here today. We have Valerie Andrew, who's working as the BWG Outreach Chair within SOSA. My esteemed colleague, Mark Littlefield, who's heading up the TWG Small Form Factor Subcommittee, and that's readily obvious from that title. We've got a lot of acronyms in SOSA to deal with. And then I work in the Hardware Subcommittee, and a couple other notable folks that we have working towards this effort, Dave Caceres, who's a manager of Embedded Computing Group, and Gary Hansen, who's our subject matter expert on chassis management. So I want to take a minute and explain this partner ecosystem slide. What's this all about? Really, if you take a look at this slide, and if I look at the sponsors behind me, we got a lot of the same people sponsoring this event, as well as if I look at the ecosystem of partners that we work with to integrate and develop systems, they're a lot of the same folks. What's important is if we're going to get to a place where we can get to interoperability, we all got to work together. If we don't work together to prove out payloads and prove out connectors, backplane implementation and things like that, we're not going to be able to demonstrate that we're able to make interoperable systems. So looking at what's taken place over the year in 2022, and keeping in mind that we're coming right out of the pandemic, there was, I think, a wave back in early 2022 that actually canceled this event. We kind of kicked it off with the Tri-Service Open Architecture Interoperability demonstration, a mouthful. And that was a really neat event. There was like 40, 45 organizations at it demonstrating interoperable systems. And I was surprised to see how many interoperable systems were actually there, quite a few. And there were some really great booths. As a matter of fact, the Curtiss-Wright booth was really interesting. They rolled in this like portable lab and must have had 5 or 6 really interesting demonstrations. And I think that'd take Alcove over in the corner because they overflowed. So they had some really great stuff to see. Unfortunately, my pictures all have Elma stuff because you had time to run around and take pictures of everybody else's stuff to put in these slides, so you have to bear with us. We also sponsored the Face Open TIM last year as Elma, which was a sort of a milestone for us because we'd never done anything like that. And that was an interesting event. We also had about 50 attendees demonstrating interoperable systems and products and software solutions and things like that at the Face SOSA TIM. It was very well attended. It was a great event, and thanks to Boris in marketing for stepping up and taking us to the sponsorship level, being able to participate in that fashion. So at the end of the year, that recaps with AUSA, where we try to get together some demonstrations of system technology that's useful and interesting when you consider the goals of the Tri-Services and what they're trying to get done. So we came up with a couple of demonstrations to take to that we started with at the Face SOSA TIM, and we sort of ended up at AUSA at a really well-attended exhibit. And at this time, there were very few masks, and it was really great to see everybody getting out and about. So who's leading? So if you look at this objectively and see who's really bought into MOSA, from our perspective, we think it's the Army. The cavalry's in the lead, so go Army. So that takes us to a list of initiatives that are associated with the Army. And when we were at the Tri-Service event, what we were told by Army leadership was to get to know a new term. And that term was CMFF, CMOS Mounted Form Factor. And it took me about 5 or 6 tries at this to get this down, because all I have in my head is CMOS, and now they want us to know a new thing, and it's like CMFF, and what's that about? Well, that's about creating a chassis that's based on CMOS and SOSA, and folding into the Army's vision of where they're going. The interesting thing about this is the Army was telling us they're totally bought into MOSA and SOSA and CMOS, and they need it to reach their objectives going forward. So what came out of that was the CMFF RFI for the CMOS mounted form factor. This was back in the March timeframe, and I think it was deliverable in May. Army was stressing something called the SAVE IDD. That's the space claim that the box can take, and it also is conditioning around the box relative to its mounting, so that boxes can be mounted in the various vehicles that the Army is going to deploy, and that there can be interoperability at sort of the packaging level. So the focus around that, from what we understand, is Block 1 system requirements or capability set 25. And what that's doing right now is really driving the industry to develop CMFF solutions. If we look at boxes that were at AUSA and TSOID, we're starting to see early indications of this. I'll just point to Curtiss Wright. Curtiss Wright had a really couple of interesting chassis in their booth. One was sort of a side-by-side cooling technique where they had 2 stacks of boards inside a chassis that I understand meets the SAVE IDD, at least the first cut. And then they also had a neat little green box. We have a green box we call the Little Green Monster. They had this little green box that is also, I think, SAVE aligned as far as footprint, but it's built in a different orientation. So it's like vertical, and it has I think it's top load. So it's a little bit of a different implementation. But what we're seeing is folks starting to deliver initial chassis that do meet the SAVE format that are required by CMFF. Another interesting program that came out this year was U360, which is 360-degree situational awareness and targeting program. That requirement is driving the needs for other technology like GPUs, high-speed Ethernet switches, and AI. So what's the Army doing with respect to getting these things tested and sort of kicking the tires on technology? What they've done is stood up something called X-Tech competitions. And a few different folks that are in this room I know work towards that or attended them. And what they're about is inviting people to come or organizations to come and test their wares against a set of requirements that the Army stands up. So the first one that we went to was the PNT chassis switch X-Tech competition in the fall of 21. That was really about PNT cards and also chassis, or also, I should say it's about PNT cards and switches. I don't think this was the chassis level. And it did encompass development E-frames, so they were looking at those resources. But it gave a set of standards to evaluate those technologies against. The next one that happened was CMFF A-Kit in fall of 22. And that just finished, and I think the folks who finished in the finals were actually just released. And the interesting thing about these competitions is you actually get paid to do it. That's like new. So you go in the Army, if you finish in the top 3, I think even if you show up, you get some sort of compensation. And if you finish in the top 3, you get a fairly substantial payment that helps defer the cost of attending the X-Tech competition. So this is a kind of neat thing. And last thing I wanted to highlight is I should say PNT oil, is the Precision Navigation and Timing Lab. And this lab's being used as a laboratory set up by the Army where you can go and support test and integration, and where they can invite people to come in and do some work to see how your product's working. So the CMFS development, the Army's rolled out a phased approach to that. I just wanted to highlight sort of where we're at. as industry in answering the needs of CMFF. We're at the block 1 phase, where they've broken this up into 3 phases going forward around CS25. So here I wanted to bridge back to what CS25 really is. What the Army's informing us of is what they need for their next major set of milestone efforts to get to and through CMFF integration. And what they're telling us over here is what payload cards they want, power, network, security, et cetera. And then the requirements, they get progressively more difficult as time goes on to achieve the objective. So this gives us an idea of, as industry, what the Army is going to be driving us to and what we have to help support to support the Army in reaching their goals. CMF forward path for ground vehicles. This is right out of the Army reference architecture. Shows the need for a scalable CMFF chassis where you're going to have different payload count. Here, 5 payload, 7 slot. And then the next one, 8 payload, 11 slots. That drives 2 new topologies. So the topology for the smaller system is 7 slots. It's 6 slots plus 1 power supply. And this is a notional topology diagram from Elma, not from the Army. And over here is a notional diagram of an 11 slot. This is all based on SOSA-aligned slot profiles, payload, I/O, the I/O-intensive SBC, switches, and then I think that's pretty much it. And then the power supply. Here you see that there's less payload slots, and in this one there's more payload slots. But the bottom line is this all has to fit into the SAFE format. And this is an example of an ATR we recently upgraded to CMOS 2 backplane that supports 25 gig paths and supports current slot profiles that are designed by SOSA, along with a notional save tray. So that's a little bit better view of it that we had at the SOSA TIM and at AUSA. What we're doing here is using a CMOS 2 backplane that's current, that's aligned with SOSA 1.0 profiles. It's set up for a wide range V262 power supply, and of note here is that the power supplies that largely have been built today won't meet the specifications that the Army's dropped in CMFF. That's because of things like cranking voltage and vehicles that run sometimes off of just batteries, and what happens when you start a vehicle, where you're going to need a really wide input range, so that's something new. It's useful in this box. It's useful for payload testing as we progress forward, and it's sort of an interim step towards a fully compliant CMFF box. So what were the challenges? Well, challenges are obviously swap C, and I think the reference architecture had quite a few companies responding to it with really quite stringent and tall requirements from the Army to sort of meet their objectives. Swap C is one, TDP is another. The box constrained to 600 watts total. The environmental requirements are wide because these boxes have to operate in just about every environment in the Earth that you can think about. So you have very wide environmental requirements. Stringent power supply requirements, we talked about that. Some of the other things that have to be met are filtering and hold-up time, which causes you to think about how much energy you can store in a power supply versus where you might have to locate that hold-up capability. This power supply I'm showing here is sort of the next step towards those goals from Bellman that does have a wide input range and it does have certain hold-up capabilities. And lastly, the box has to be very rugged, driving against requirements for shock, vibe, and immersion, which is actually getting it wet, which makes it a lot harder to do. So another new initiative is around sensors with the U360 situational awareness program. This is what is driving, or what's needed is GPGPU, and when you think about it, high bandwidth interconnect on Ethernet, because you're going to move the data from sensors that are going from 1 gig to 10 gig. You got 10 gig input pipes that now have to manage data in a network and then deliver it to processing resources within the CMFF box that will be able to keep up with the demand. So a couple of things that we worked on this year that are in that vein is an AI object recognition demo, What we did was partnered up with ISO, who's partnered with NVIDIA, and Concurrent Technologies to do an AI demonstration. And what this demonstration did was take a GR2 RTX 5000 Turing GPGPU and couple it with a CCT TRMA6 ICE, like the multi-core compute-intensive SBC. So in SOSA or CMOS, you've got the compute-intensive slot profile for the processor, and then we actually put the GPGPU in another compute-intensive profile in this case. And then we wired that up with Meritech cables in the back at Gen 3, not at Gen 4, to be able to run this demo. So the system ran an AI application that had a trained neural network in it. We were able to stand this demo up when I would call record time. It was amazing how fast we could do certain parts of this because of the standardization relative to how the boards are made and how we could couple them to an off-the-shelf chassis that almost brought to the market and get that integrated together. The next demo that we did, I think that's relevant to the discussion today, is an Ethernet performance demo that compared the performance of 110 40 gig switch networks against 110 40 and 100 gig. Now, to be fair about this, at 100 gig, the measurements were taken with back-to-back TRMA6 boards, and the other measurements at 40 gig were taken across a network that had the processors in a fabric with a switch. So we're actually able to do more of a real-world comparison. So I'll show you the results of that in a second. I think the trend here is that GPGPUs are moving from Turing to Ampere architectures, where the demands in the processing environments that are coming up are going to focus on the higher performance architecture that Ampere brings to the table. And then you can see here is the AI demo where we've got a pre-recorded video stream that's being analyzed by or processed by the GPGPU against a trained model with a TRMA6 taking the data stream from this camera, digitizing it, and then passing that data through memory over to the GPGPU to have it processed. This application actually ran multiple demonstrations where the object recognition against the CAN data was one, and then it also did object recognition against the video stream from the camera that was being digitized by the processor. And then lastly, here's the sort of the hard results of what the Ethernet performance demo was able to bring to bear. There's a little meter here that showed throughput at a gigabit. I think you had about 112, I think it was around 112 megabytes per second. But this is a typo. At 40 gigabytes per second, actually, or 40 gigabit, we had 2.8 gigabytes per second throughput. At 100, we were able to do without RDMA around 5 gigabytes per second, and with RDMA 9. So if you look at the comparison, this is roughly 2 to 1, and this is roughly 3 to 1. So that's what we'll be able to see when we move up to 100 gig. We still have work to do to prove this out. We didn't have the full 100 gig network infrastructure to use to do these tests. So that's a goal going forward in 2023. So what's next? So for the industry, and this is in Elma terms, we have saved aligned chassis progression, meaning CMFF aligned chassis. What are we going to do to get there? So what we have now is, this is sort of where we're at, is this is our old CMOS 1 ATR that's been used for testing events over the years. And this is the upgraded one that we had at AUSA, where we started to show the save tray. And over here, we've got a notional view of what a CMFF chassis might look like that's scalable, sealed, and more ruggedized. And it'll probably change, but that's a sort of first cut, so we just wanted to share that. And lastly, scalable backplane architecture. What needs to be done in backplanes? We need to go to a backplane that supports 1 power supply and 6 slots, so that'll be a 7-slot topology. What we'll do is cast up from development backplanes that we have now that do operate and support 25 gig differential pairs, or that infrastructure that can support up to 100 gig switches and payloads. And here we have a CMOS 2 backplane now that's 12 slots. This can get scaled up either to 11 or to 13, because there is a larger topology that's supported by CMFF I think for platforms aloft, but I'm not quite sure that's the intention. And that's about it. So where we've gotten in a year as an industry is, again, I think pretty amazing what's been able to get done. Tons of interactive demos at Tri-Service event and at the SOSA TIM. So I think this is really starting to show that SOSA and MOSA and the efforts that have taken place over the last 5 years are starting to bear fruit. We're able to integrate demos in much faster times than we were able to do that before, and I think this is also a benefit of coming from benefits of the standard. We see the service branches adopting and telling us what their paths to market are going to be, or paths to their deployable products are going to be, leveraged around or using the SOSA 1.0 technical standard. We see benefits from the community expanding by a larger number of products. We had over 50 vendors at the FACE and SOSA TIM. And with that, I think I've gotten to the end. So stay tuned for another exciting chapter from the book of MOSA. Thank you.